As mentioned briefly in the previous main video, link below, normal stresses differ from shearing stresses in that the direction of the stress is perpendicular to the cross-section area they affect for normal stresses and parallel to the cross-section area they affect for shearing stresses. Direct shear occurs when two volumes of the same member have components of the external loads pointing in opposite directions. The simplest example, although direct shear is not limited to this scenario only, is when a member is subjected to two opposing transverse forces. This is a common situation that happens when a bolt is connecting two members that are subjected to forces that are trying to pull them away from each other. This and other scenarios where direct shear occurs will yield a shear stress equal to the load V over the transverse area A. In this case, we use V to refer to a shear force and differentiate it from a normal force P. Notice that this shearing stress, just like any other type of shearing stress, namely the torsional shearing stresses and the transverse shearing stresses, are denoted with the Greek letter tau. Also notice that the stress in this case is V over A, not 2V over A. A free body diagram of the resulting body at either side of the cut clearly shows the internal shear force V that affects the area, and again, notice that the force is parallel to the surface of the cut. The shear force that causes a direct shearing stress is whatever the internal force results in after doing a proper free body diagram. So for example, inside a more complex structure that is subjected to a pulling force F, we can calculate the shearing stresses inside the bolt at two different locations. The free body diagram of the section of the bolt that is relevant to find the internal shear forces would show us that the left surface with an area of pi d squared over 4 is subjected to half the load F. The shearing stress for the surface on the right would be subjected to the other half. Defining normal and shearing stresses is important to find the components of a stress, or what is its equivalent, components of external loads that are perpendicular and parallel to the plane of interest, to calculate the resulting normal and shearing stresses. For example, if two rectangular cross-section metal pieces have been glued together using a plain scarf joint, and the new prismatic member is being subjected to tension, there would be interest in finding the normal and shearing stresses at the slanted surface to be able to compare them to the maximum allowable stresses that the glue can withstand. We've already seen that for normal stresses, we might be interested in comparing them to the yield strength or the ultimate strength of the material. But we'll learn that there are many other maximum allowable stress/strength values that we must consider when comparing the stresses that we calculate. In this case, we want to find stress values at the glued surface because 1. The maximum allowable normal and shearing stresses of the metal are probably higher than those of the glue, so if this part breaks apart, it'll most likely be because the glue didn't hold, as opposed to the metal actually breaking. And 2. We want specifically the normal and shearing stresses with respect to that inclined surface where the glue is, because what we can probably find as properties for the glue are the maximum allowable shearing and normal stresses, not some random inclined stress at an angle that would result from the external load direction on that slanted surface. This stress component method is also applicable to finding the normal and shearing stresses of infinitesimal cube elements within any member or structure. The reason this is important is because specific combinations of normal and shearing stresses generated by orthogonal external loads in 2D or 3D can result in even larger values of normal and shearing stresses depending on the angle. This is what will be known as principal stresses in plane maximum shearing stresses and overall maximum shearing stresses. But we'll learn about these and more circle in a much later video, link in the description below. For now, all we need to understand is that a stress, just like a load vector, can be decomposed into orthogonal components. In the case of this glued member, the normal stress would be equal to either the normal component of the force over the entire glued area, or the whole force vector over the 3D projection of the area that is perpendicular to the load. However, since what we most likely know about the setup is the magnitude of the external load P and the dimensions of the non-slanted cross-section area, it makes sense to write the normal component of the stress in terms of P and A. The normal component of the load P is, from alternate interior angles, complementary angles, and the fact that cosine is the adjacent side over the hypotenuse, equal to p cosine of theta. Using the angles that we see here and using the same cosine definition, the slanted area A sub theta is equal to A over cosine of theta. This yields an expression for the normal stress on an oblique plane. And remember that this expression only works if the angle you know is that between the cross-section and the oblique plane, in this case theta. If the angle you have measured or have been given is that between the external plane of the member and the slanted plane, in this case alpha, then you would use sine instead of cosine. The shearing stress would be equal to either the component of the force vector that is parallel to the slanted surface over the entire glued area, or the full force vector over the projection of the area that is parallel to the load. Following the same process from before with the normal stress, and realizing that what you probably have is the dimensions of the cross-section area, not the slanted one, and the external load P, we'd see that the component of the force that is parallel to the slanted surface, in this case labeled V for shear force, is P sine of theta. And since the slanted area hasn't changed, it is still A over cosine of theta. The expression for this shearing stress would be P over A times sine times cosine of theta, which, if you remember your trig identities, can be simplified to P over 2A times sine of 2 theta. And again, this expression only works if the angle you have is that between the cross-section area and the oblique plane, in this case theta. If you have the complementary angle, then all you need to do is find theta by subtracting that angle from 90 degrees. Finally, just like we defined normal strain as the changing length over the initial length, and that is for the engineering normal strain, the shearing strain is defined as the angle gamma through which the faces of a deformed strain element have rotated. This can either be the angle between the undeformed and deformed sides when the other two have not rotated. Notice that the horizontal faces have not rotated, or the sum of the angles for when all the faces have rotated due to a shearing stress. The notation we use for shearing stresses has sub-indices that correspond to the face and direction the vectors affect. For example, on the y face or top face, there is a vector facing in the x direction, and therefore the shearing stress is tau yx on the top and tau xy on the side. And of course, for this element to not be rotating, these two values are the same. By convention, we say that a shearing stress is positive if both vectors are pointing towards the positive directions of the axes, which is usually the top right corner for standard positive directions of x and y. For an element that has two faces that do not rotate, this shearing strain, angle gamma, can therefore be calculated using the tangent of the displacement of one of the faces and the distance between those non-rotating faces. And since these shearing strains are usually small and gamma is in radians, not degrees, the tangent of gamma is similar to gamma itself. This comes from the fact that the limit of sine of x when x approaches 0 is x, or similar limits like sine of x over x being 1. And just like with the elastic modulus, the shear modulus or modulus of rigidity G can be defined as the ratio between the shearing stress and the shearing strain, as long as the material is subjected to elastic deformations. The relationship between shearing modulus and elastic modulus will be given by Poisson's ratio, but more on that later. Link below if you're interested. Let's take a look at an example where we make use of what we've learned today. Two rigid horizontal plates are bonded to a rectangular block that has a shear modulus of 90 ksi. The lower plate is fixed, while the upper plate is subjected to a horizontal force P. If we know that the upper plate moves 0.04 inches under the action of the force, what is the average shearing strain in the material and the value of the force P? Before continuing to watch the video, try to find the solution to these questions on your own. The same advice goes for the additional example videos on this topic that are linked in the description below. The answer to the first question is pretty straightforward. We know that gamma will have almost the same value as tangent of gamma, which would be equal to the horizontal displacement of 0.04 inches over the vertical distance between plates. For the second question, we know that the force P is what's generating that shearing stress tau. The area is the area that is parallel to the force, and the shearing stress can be calculated by multiplying the shear modulus times the shear strain. With the given value for the shear modulus and the shear strain that we just found, we find the value for the shearing stress and with it the load P. For more examples regarding direct shearing stresses and shearing strains, including some where normal and shearing stresses are calculated for oblique planes, make sure to check out the links in this video's description. Thanks for watching.